Hi, this is Ashley Bedford, founder of the Runtime Diaries, and I am super excited for this one. It's day 15 of our hashtag 30 Days of Code Challenge with Educative. And we have today similar string groups. So let's get into this hard question.
Today, we're unpacking a hard problem from LeetCode. But don't worry, when you strip away the noise and reframe it correctly, it becomes a beautiful graph connectivity challenge. This is similar string groups, where we count how many connected components exist based on a very specific definition of string similarity. Hard problems often feel hard because they're disguised as something else. Our job is to see through that disguise. We're given a list of end strings. All the strings have the same length. That's important. Two strings are defined as similar if they differ in exactly two positions, or if they're completely identical. Our goal is to count how many groups of mutually similar strings exist. Now here's the key insight that makes this problem solvable. Even though we're looking at strings on the surface, the hidden structure behind the problem is a graph. Each string is a node. Two strings are connected by an edge if they're similar. And the question becomes, how many connected components are in this graph? Let me define similar more precisely, because this definition is critical to solving the problem. Two strings are similar if one of these conditions is true. The first condition is they're completely identical. Every character matches. That's easy. The second condition is that they differ at exactly two positions, and swapping those two characters in one string produces the other string. Let me give you a concrete example. Take tars and rats. Let's line them up character by character. At position 0, we have T versus R. They differ. At position 1, A versus A, they match. Position 2, R versus T, they differ. Position 3, S versus S, they match. So they differ at positions 0 and 2. Now, if you swap the characters at positions 0 and 2 in tars, you get rars. Wait, that's not right. Let me think about this differently. Actually, for the swap condition to work, tars at position 0 must equal rats at position 2, and tars at position 2 must equal rats at position 0. Tars of 0 is T, rats of 2 is T. They match. Tars of 2 is R, rats of 0 is R. They match. So yes, tars and rats are similar because you could transform one into the other by swapping positions 0 and 2. From a graph perspective, each string is a node, and an edge exists between two nodes if those strings are similar according to this definition. Let's walk through the classic example to see how groups form. We have 4 strings: tars, rats, arts, and star. Let's check which pairs are similar. Tars and rats, we just verified these are similar. That's one edge. Rats and arts, let's see, at position 0, R versus A is different. Position 1, A versus R is different. At position 2, T versus T is the same. And at position 3, S versus S is the same. They differ at positions 0 and 1. Check if rats of 0 equals arts of 1, and rats at position 1 equals arts at position 0. R equals R and A equals A. Yes, they're similar. That's another edge. Tars and arts, you could check this one differently, but here's the beautiful part. We don't need to. Tars is connected to rats, and rats is connected to arts. That means tars, rats, and arts are all in the same connected component, even if tars and arts aren't directly similar. That is transitivity. If A is connected to B and B is connected to C, then A and C are in the same group. Now, let's check star. Star compared to tars, all 4 positions differ, so they're not similar. Star compared to rats, multiple positions differ, so they're not similar. Star compared to arts, multiple positions differ, so they're also not similar. Star has no edges. It's an isolated node. That makes it a separate group. So we have 2 groups total. Group 1 contains tars, rats, and arts. Group 2 contains just star. Once you treat each string as a node, the problem becomes how many connected components are in this graph. You can solve that with standard graph algorithms. You have 3 main options: DFS, or depth first search. Start from an unvisited node. Explore all connected nodes recursively. Mark them as visited. Each time you start a new DFS, that's a new component. BFS, or breadth first search. Same idea as DFS, but you explore level by level using a queue instead of recursion. Union find, also called disjoint set union. This is a specialized data structure for tracking connected components. You union nodes together when they're similar, and at the end, you count how many unique root parents exist. Union find is the cleanest and most efficient approach for this problem. So that's what I'll focus on today, but all 3 methods work. A lot of people get confused by this problem because they approach it the wrong way. They try sorting the strings alphabetically, thinking that will group similar strings together. It doesn't help. Similarity isn't based on alphabetical order. They compare only adjacent strings in some ordering, missing connections that exist elsewhere. They treat the problem like anagram grouping, where you group strings with the same characters. That's a completely different problem. They forget that similarity is transitive. This is huge. If A is similar to B and B is similar to C, then A and C belong to the same group, even if A and C aren't similar directly. The key idea here is that similarity spreads through the network like friend of a friend. You don't need direct similarity between every pair in a group. You just need a path of similarities connecting them. Let me walk through the baseline approach so you understand the structure of the solution. For every pair of strings I and J, compare them character by character. Count how many positions differ. If the mismatch count is 0, they're identical, so they're similar. If the mismatch count is 2, check if it's a valid swap. If so, they're similar. If the mismatch count is anything else, they're not similar. Once you've checked all pairs and built a graph of connections, run DFS or BFS to count how many connected components exist. The time complexity for this approach is O of n squared times L, where n is the number of strings and L is the length of each string. You're comparing n squared pairs, and each comparison takes up to L time to scan through the characters. This might sound expensive, but it's actually the expected complexity for this problem. We'll talk about why in the next slide. This problem is inherently quadratic. Here's why. In the worst case, if many strings form one giant connected component, you must compare a lot of pairs to discover all the connections. Think about it. If you have 100 strings, and they're all connected in one big group, you need to check potentially thousands of pairs to build that group. There's no magical shortcut that avoids this. You can't look at a string in isolation and know which group it belongs to. You have to compare it to other strings. So O of n squared times L is not a sign of an inefficient algorithm. It's the nature of the problem. Optimizations can reduce constant factors, like exiting early when you find more than 2 mismatches, but they don't change the O of n squared nature of checking pairs. Even though we can't avoid checking many pairs, we can make each individual comparison as fast as possible. Here's how to check if 2 strings A and B are similar. Loop through the characters one by one. Keep a counter for how many positions differ. If the mismatch count exceeds 2, stop immediately and return false. There's no point checking the rest of the string. You already know they're not similar. If you reach the end and the mismatch count is 0, they're identical. Return true. If the mismatch count is exactly 2, verify the swap condition. Check that A at position I equals B at position J, and A at position J equals B at position I, where I and J are the two differing positions. If that's true, return true. Otherwise, return false. If the mismatch count is 1 or greater than 2, return false. This early exit trick, stopping as soon as you find a third mismatch, saves massive time and practice. Even though the worst case complexity is still O of L, the average case is much faster. Let me explain the DFS approach in more detail. First, build an adjacency list. For each string, store a list of all other strings it's similar to. This requires checking all pairs, which takes O of n squared times L time. Second, maintain a visited set to track which strings you've actually explored. Third, for each unvisited string, start a DFS from that string. The DFS explores the entire connected component, marking every string in that component as visited. Fourth, increment your component counter. Each time you start a new DFS, that's a new group. After you've visited all strings, your component counter is the answer. This approach is intuitive and easy to visualize. The downside is that building the full adjacency list can consume a lot of space. In the worst case, if all strings are similar, you'd need O of n squared space to store all the edges. Union find is the optimal approach because it avoids building the full adjacency list. Here's how it works. First, initialize a union find data structure with n elements, one for each string. Initially, each string is its own parent. Each string is in its own group. Second, for each pair of strings I and J, check if they're similar. If they are, perform a union operation. This merges the two groups that I and J belong to. Third, after checking all pairs, count how many unique root parents exist. Each unique root represents one connected component, which is one group. Why is union find so powerful here? There are two reasons. The first is path compression. When you perform a find operation, union find flattens the tree structure, making future operations almost constant time. Second, union by rank. When you union two groups, you attach the smaller tree to the larger tree, keeping the overall structure shallow. These operations mean each union or find operation takes O alpha of n time, where alpha is the inverse Ackermann function. For all practical purposes, alpha of n is a tiny constant, like 4 or 5, even for enormous values of n. So union find gives you O of n squared times L times alpha of n complexity, which is effectively O of n squared times L since alpha of n is essentially constant. And it only requires O of n space for the parent and rank arrays compared to O of n squared space for a full adjacency list. Let me put all three approaches side by side so you can see the trade-offs. DFS is O of n squared space for the adjacency list, O of n squared times L time complexity. Best for visual understanding and when you need to explicitly explore the graph. BFS, same as DFS, just iterative instead of recursive. Some people prefer iterative solutions to avoid stack overflow on deep recursion. Union find is O of n space and O of n squared times L times alpha of n time complexity, which is effectively O of n squared times L. It's best for production code and when you just need to count components without explicitly exploring them. Alpha of n, the inverse Ackermann function, grows so slowly that it's basically constant for any realistic input size. So while all three approaches are correct, union find is the most elegant and efficient. Let me summarize the core insights that make this problem solvable. First, you must compare string pairs. There's no way around this. The problem is fundamentally quadratic. Second, similarity creates edges in a graph. Once you see the graph structure, the problem becomes much clearer. Third, connectivity is transitive. If A connects to B and B connects to C, they're all in the same group. Fourth, union find avoids building a full graph. You don't need an adjacency list. You just need to track which groups have been merged. Fifth, early exit when the mismatch count exceeds 2. This reduces the average time per comparison significantly. And sixth, the number of groups equals the number of connected components, which equals the number of unique root parents in union find. Let me walk through the earlier example using union find so you can see exactly how it works. We have 4 strings: tars, rats, arts, and star. Let's assign indices. Index 0 is tars, index 1 is rats, index 2 is arts, and index 3 is star. Initialize union find. Each string starts as its own parent. So parent of position 0 equals 0, parent of position 1 equals 1, parent of position 2 equals 2, and parent of position 3 equals 3. Now, check all pairs. Compare 0 and 1, tars and rats. They're similar. Perform union of 0 and 1. Now, both 0 and 1 point to the same root. Let's say root is 0. Compare 1 and 2, rats and arts. They're similar. Perform union of 1 and 2. Now, 2 also points to root 0. All 3 strings, 0, 1, and 2, are in the same group. Compare 0 and 3, tars and star. Not similar, so there's no union. Compare 1 and 3, rats and star. Not similar, so there's no union. And compare 2 and 3, arts and star. They're not similar, so there's no union. At the end, count unique roots. We have root 0, which represents the group containing 0, 1, and 2. And we have root 3, which is just 3 by itself. 2 unique roots, 2 groups, and that's the answer. Let's cover some edge cases to make sure your solution is robust. A single string. If there's only one string, the answer is one group. That's a trivial case. All identical. If all strings are identical, they're all similar to each other, so the answer is one group. All different. If no 2 strings are similar, each string is its own group, so the answer is in groups. Length 1 strings. If all strings have length 1, only identical strings can be similar. You can't have exactly 2 differing positions if there's only 1 position total. Large L values. When strings are very long, the early exit optimization becomes essential. Without it, you'd waste time scanning hundreds of characters even when the first few already show more than 2 mismatches. Let me summarize the final complexity analysis. You need to check roughly n squared pairs of strings. You can't avoid this in the worst case. Each comparison takes up to L time to scan through the characters, though early exits make the average case faster. Each union or find operation in union find takes O of alpha of n time, which is effectively constant. Total time complexity is O of n squared times L, and the space complexity with union find is O of n for the parent and rank arrays. This is optimal. You cannot improve on O of n squared times L asymptotically because you must check enough pairs to discover all the connections. Let me give you the key takeaways that will help you solve similar problems in the future. First, reduce the problem to connected components. Recognize that similarity creates a graph and groups are components. Second, use mismatch counting to detect similarity efficiently. Count differing positions and exit early if the count exceeds 2. Third, use union find to avoid building a full adjacency list. It's cleaner, more efficient, and uses less space. Fourth, expect O of n squared times L time complexity. That's the nature of this problem. Don't waste time looking for a subquadratic solution that doesn't exist. Fifth, count unique root parents to get the final number of groups. That's how union find gives you the answer. Sixth, hard problems get easier when you reframe them correctly. This problem looks like a string problem on the surface, but it's really a graph problem underneath.
And that's a wrap for day 15. If you like this video, like it down below, share it with a friend, subscribe to our channel. We'll be bringing a lot more breakdowns shortly, so we hope to see you soon.